Mr. Starkey, and we're going to continue talking about biomechanics and specifically how geometry and the human body are inextricably linked together. So we discussed earlier about how the body is kind of like a machine. It has moving parts. It has all the features that would be included in any kind of machine. So you have things like segments. Okay, so like the bones are kind of like the segments of this machine. You have things like hinges. Obviously, the joints serve as that purpose as a hinge. You have the levers, so you have the ability for the combination of a hinge and a segment to create leverage on something. And you have all these pivot points throughout the body. And that is kind of how we have to think about the human body as a machine. And we're going to talk more about that specifically as it applies to the geometry of movement. Okay, so movement is always, almost always can be measurable in degrees. Okay, so it can get very complicated and it can be also very simple. Again, we have all sorts of things to analyze within the human body. So a segment might be something like this shin here. Okay, so the shin is an example of a segment, or the femur, the thigh, would be an example of a segment. The upper arm would be a segment. The forearm would be a segment. We can look at things like the center of mass. In the case of this athlete, his center of mass is probably about where my cursor is right now. That refers to the point at which they would tip over one way or the other to stay balanced, kind of like a teeter-totter. And then we have the center of joints. Where do we analyze the middle of a joint? Here you see these little dots that represent the middle of the joints in this very complicated image. And then we have these things, these terms we're going to talk about later, which are relative angles and absolute angles. So a relative angle is the angle between two independent segments. Okay, so if we look at this graphic on the right, we can see as this person is squatting, they go from about 180 degrees here at the top to about 45, 47 degrees at the bottom. Okay, so in the case of looking at the knee joint in this way, we are looking at the constantly changing angles between the shin and the thigh. An absolute angle would refer to something fixed in space. So for example, in this diagram, which is kind of a blown up version of our previous ones, these dotted lines here refer to the 0 degrees. So okay, so if we were to say drop a string down and hold it right over this ankle joint, so if we were to drop a 0 degree line straight from above us, that's what this dotted line represents. So the angle between 0 and the shin is represented here at 49 degrees. You can really do this lots of different ways. It can be from a 0 degrees, or what's sometimes referred to as a plumb line in construction. It could also be from the ground. It could be from this parallel to the ground position here. So draw that at 0. So if you think about these relative versus absolute angles, we have some common terms we see sometimes especially in weightlifting, called a parallel squat or a 90-degree squat. So as you're looking at this image to our left, I want you to think, is this a 90-degree squat? Is this a parallel squat? Okay, is this below 90 degrees? Okay, well, it depends, because we have two things to look at. If we look at the relative angle, we'll see that it's actually 73 degrees at the knee. So this knee angle here is 73 degrees if we look at the center of the ankle, center of the knee, center of the hip. So we're roughly a 73 degree knee angle. So certainly it's below 90 degrees as a squat. If we look at this person, we'd ask the question, are they squatting close to 90 degrees? Most of us would say they're not squatting low enough, or at least I hope so. And officially, we would have to say, yeah, I mean, she's squatting almost 90 degrees, but are we seeing this word parallel, which would imply something totally different? So specifically, here's a woman that's squatting with their thighs, what we would most often say parallel with the ground. So we have a 90-degree angle if we think about the 0-degree point being up here. 0 degrees, from 0 degrees to the center of the knee, to the center of the hip, we have a absolute angle of 90. And here we have a relative angle of hip, knee, ankle of 72 degrees. So when people talk about squatting to 90 degrees, well, are they talking about the absolute angle 90 degrees, or are they talking about the relative angle of the knee? So we get to this point about, how do we count the angles? Obviously 360 degrees is how many degrees that are actually in a full circle. But in biomechanics and in sports, oftentimes we have to think about this a little bit. And in my experience, I would tell you right here is that it depends on who you're talking to. So for example, if I was to tell somebody that a pitcher from behind is throwing at 230-degree arm angles, a lot of you would go 230 degrees. Again, if I took 0 down here and I measured all the way around the compass, we have a absolute angle of 230 degrees. Okay, roughly kind of like what you see in one of these photos here. But the question you have to ask yourself is, does that even make any sense? Because if I'm telling a baseball hitting coach, or sorry, a pitching coach, say when you look at your athletes from behind, look at about a 230-degree angle is what we're looking for the normal curve or angle for the release arm. A lot of coaches are going to be very confused. Versus, let's say, taking it straight off of this edge here, now we have something more like a 40-degree angle. Or if I dropped it down from here, I would have a 50-degree angle. Again, it really depends on who's looking and what's normal for the sport. I can tell you right here, when it comes to something like baseball overhand throwing mechanics, from the posterior view, you definitely will see this 0 degrees coming from up here. So we take 180, subtract 230, and on this compass here, we would be reporting something like 50 degrees instead of what you see here at 40. But it's also possible, if you draw your dotted line parallel to the ground, you could say 40 degrees and you wouldn't be wrong. So we're going to look at this bicep curl, a very common exercise. And I, again, am answering this question whether we use a 180-degree scale or we use a 360-degree scale when we're talking about degrees. Well, if I'm judging somebody doing this exercise in the weight room, I'm going to be telling them, hey, you start at about 180. So right here, we start at 180, you're halfway at 90, and you finish at about 60, 50 degrees. If I tell you that your arm's at 180, most of you know exactly what I mean, straight arms. And if I tell you to move your arm up to 90 degrees, you'd be thinking about a right angle. This is a very common approach to looking at these, whether they are 180 or 360. Adversely, if I put 0 at the bottom, like when we get a compass and we actually see all the radians and degrees listed, we would never say, oh, well, once you start at 290 and you want to finish at about 180. I mean, if I said that to someone in the weight room, no matter how experienced they are, they would probably be extremely perplexed. So you might be asking yourself, so what? Why does this even matter? Well, there's lots of practical implications for understanding how the human body moves and how the skeleton moves and how these joint angles are calculated. By being able to observe a 3D motion capture of a human being by looking at the X, Y, and Z coordinates of their joints, we can reconstruct 3D animations. So many of the things we see in video games or in major motion pictures have been done by people who have a very solid understanding, probably even doctors in biomechanics and kinesiology, or the study of movement. Another practical use for this would be in athletics. Here's a very famous study where they're examining how people in wheelchair basketball were able to do basketball shooting. Because in wheelchair basketball, clearly you're not going to jump up like a professional basketball player would be able to do. So it really does come down to arm mechanics. So they studied all sorts of different things. They studied the shoulder horizontal adduction. Sorry, let me go back to that. They studied internal rotation of the wrists. They studied the angle of the elbow. So elbow extension and flexion. You can read this down here. Shoulder abduction, wrist flexion, supination, forearm pronation. And by doing this, they're giving coaches tools to be able to tell the athletes how to shoot the ball better, more accurately, more consistently. Another real practical thing is we're seeing an emergence of robotics. Well, as we try to, there's a big push in robotics to try to replicate the abilities that everyday humans have. And right here, this bot on the left, this is probably like $1 million project to get a robot to walk in tennis shoes like a human. And because the machine's not designed as well as we are in many cases, and it's been quite a challenge for engineers to figure that out. Or in the case of this experiment here by this very famous company, Boston Dynamics, they're looking to see, how can we replicate the tendency to fall and things like that when we're dealing with robots, because robots don't have the same kind of innate ability to just detect their motion. And probably the most practical reason to understand joint mechanics and radiance and angles and degrees is through understanding how it applies to us as living healthy. Here's an image of looks like a paramedic maybe, or a first responder helping lift a gurney into like a pretend ambulance. So this isn't a video overlay, but these two motion sensors on the arm and the forearm, on the thigh and on the shin, are giving the computer data in relation of these relative angles. So during their lifting mechanics, they're studying to see how they can maybe avoid injuries for somebody in such a critical position. If you've ever had an injury that may require surgery or require post-operative care or physical therapy, this is certainly something, if these doctors, physicians, and attendants or nurses, whatever, if they didn't understand how the body moves and how its joints move and these concepts of geometry, then looking at the deep tissue injury would be rather meaningless. And obviously we have people with varying levels of disease or injury that may never be able to walk again or something. So if we understood how the human body's behaving and how we might be able to design man-made machines to replicate those capacities, we can certainly help people live more productive and healthy lives.